So Paul has spoken before at one of our Winter Institutes. He's been involved with the Best Center before it was the Best Center. We've been working with Paul for probably 10 or 15 years. Long time. He did some of our original research, which is still posted on our website, still very relevant today. Some very good case studies of buildings and the role of building technicians and kind of the cultural dimension of what's going on behind the curtain. Really important, good research. He has left Pacific Northwest National Laboratory to return to his private practice, the Building Intelligence Group. And his background is heavily in retro commissioning and DDCs, controls, building automation systems, and he'll be talking about the latest innovations and trends in building automation systems this morning.
Thank you, Peter. Hello? Does this work? Hold really close.
You have to pretend you're licking ice cream.
Sounds almost obscene. Thank you, Peter. So I wanted to talk this morning a little bit about building controls and building automation and kind of the state of the art. I've been involved in the building controls industry. I actually started back in the age of pneumatics in the mid 80s, back before we had DDC controls and everything else. So I've been involved in a lot of these things over these years and a lot of changes. I'm often very critical of the building controls industry. I feel like we haven't had a lot of innovation and change. But looking back a few months ago, I thought, we really are starting to make some progress. I really see some positive things. And I often write for a magazine that some of you may or may not see called Engineered Systems. Does anybody ever see this magazine? I actually wrote a column in this magazine for about 10 years on building automation, which I stopped doing 2 years ago, and actually one of my associates writes it currently. But my editor came back and said, hey, I just had somebody cancel. Would you be good enough to write my cover story for me in November? And I thought, yeah, because I was kind of thinking about this topic, about what's going on. So some of what I'm going to talk about is covered in this article, and you can find this online or in the magazine if you're interested in what's in here. As far as my background, as Peter said, I started in the mid-'80s, about 35 years ago in this industry. I spent my first 25 years of the industry working for manufacturers. I learned the industry working for one of the major temperature control companies. I went from there to help one of the major HVAC companies build out their control product line. And it was a fantastic experience because I got to sit on the BACnet committee. I got to be involved in the standards that we created for XML and IT in buildings. And I've really gotten to travel the world and see a lot of different things. In 2004, I left industry and went and started my own consulting company called Building Intelligence Group. In Building Intelligence Group, I did a whole bunch of things. A lot of what I did is, as Peter said, is retro commissioning and energy studies. I worked a lot with owners on large-scale integration. In fact, we just finished doing a systems integration project for the third largest airport in the country on 6 million square feet of space. But I also did a lot of things that were research related. So I worked very, very closely with the national labs and with the Best Center and with projects funded by the Department of Defense and with manufacturers on advanced technology. And 2 years ago, I had an opportunity to go and work for one of the national labs. And I took an assignment working as a program manager and technical advisor for Pacific Northwest National Lab, which is the sister lab to Lawrence Berkeley Lab here in the Bay Area. And worked for them until this fall, and as Peter mentioned, I'm now back on the consulting side. Not semi-retired, I don't like to use that term, but a little more flexible in schedule and time for what I'm doing. So I have a lot of experience and interest and frankly passion about efficiency and controls and better buildings and better operation. So I'm going to ask you this question, but sitting in this room I know the answer already. What is the state of the art? How are we actually doing in the area of building automation and controls? And let's see if I can get this to work. Oh. Okay. So if we had to grade this, if you thought about what we do with commercial buildings and controls and automation, and you had to give it a grade, because you're all educators, A, being exceptional and really outstanding, and B, being decent, and C, being mediocre, and D, being starting to fail, what would you give us as a grade? A what? A D? Yes, sir.
B.
A B? D?
B.
B as in boy?
B is in boy.
You're more optimistic. Anybody else?
C is in Cleveland.
C is in Cleveland.
What's your criteria for judging it?
My criteria for judging it would be based on occupant satisfaction, based on efficiency, based on performance. So given that,
C to D.
yeah.
I fail every controls contractor that compensates for a mechanical issue.
So that's because control contractors have to fix all the mechanical issues. So I got to tell you, I've asked this question many times. I would say the median answer is that C minus. We don't do terribly well. And it's interesting. So why is it we don't do well? You know, we'd like to think of ourselves as being like on the bridge of the Starship Enterprise. This is an operations center for a building in Asia. And this guy's sitting at his fancy console and he's looking at the video feeds and the building automation and the elevators and everything else. But the reality is, you know, we just don't do that well. And why is it we don't do well? So I've thought a lot about this, and I, you know, these are the issues that I see we keep coming back with. Our performance, in general, is not great. We are not, and by the way, it was a really good question. What are the criteria? So the criteria I think about are two primary criteria. The number one reason we do controls is we need to keep the building comfortable and safe. We don't do very well at that. And the number two criteria we have is it should be efficient. And frankly, we don't do well enough at that. So I think in general our performance is suboptimal. The process we have for controls and mechanical system design and operation is a very challenging process. You know, the challenge we have going into a new building is we start with the architect. And the architect is in charge of the entire project. This is the way projects work. So under the American Institute of Architects, the architect is responsible for everything having to do with the development of that building. Well, what's the architect focused on? What's their primary criteria? Aesthetics, design, performance of the building, the general big picture scope. The details of how the systems work and how the comfort works and how the lighting and the controls and the HVAC work, that's not really their responsibility. That gets handed off to an engineer who's responsible for HVAC, an engineer who's responsible for plumbing, an engineer who's responsible for electrical, an engineer who's responsible for IT. And then as we build that building, boy, you notice everything lines up vertically. So the mechanical engineer designs section 23000, that goes out to the mechanical contractor. The electrical engineer does 26000, that goes out to the electrical contractor. And we build buildings in a way that is highly efficient, but it's highly siloed, and it's highly non-integrated. So we have the lighting system, the electrical system, we have the HVAC system, we have the plumbing system, we have the security system. Each of these goes in by a different contractor. Most of it comes in from a different supplier. And then at the end of the day, we have this person called the system integrator. You know what another name for the system integrator is? No, not the controls guy. Who's really the system integrator on most buildings at the end of the day? The operator. The operator is the system integrator, because when we get done with it, we take all of those systems, some of them have user interfaces, some of them don't, but we hand it off to the operator, and we say, now you're responsible to make sure that this building runs efficiently. What kind of training do we give the operator? We don't give them any training. Yeah, exactly. Well, actually they got 5 hours from every contractor, but they get no training at all in the integrated operation of this building. So we have challenges in that process that we use, the architects, the engineers, the contractors, and then we hand it off to the operator and we say, why is it you don't run the building efficiently? Gee, it was never meant to be. We have some interesting things going on with technology. I won't call these challenges, but these are maybe opportunities. We have this evolution going on, and I really despise this term, but I'm trying to wrap my head around it, of what we call the Internet of Things, around IoT. And you know, I was at a show last year and somebody was handing out these Amazon Echoes. So I've got one of these in my house now, and I can say, Alexa, turn on the Christmas tree lights, and boom, my Christmas tree lights turn on. Isn't that cool? I can ask her how much energy my house used, and she'll tell me. I can ask her what the temperature is in the house, or to set the security system, and she'll do all those things. Um, it's kind of clunky and clumsy, but it's simple and it works, and people are doing it in their homes. And we're going to get an expectation in the commercial world that things should work that way in a commercial building as well. Why not, right? Well, we got to figure out how to get there, because it's not quite that simple commercially. I did a project a few years ago, and I had the guy. It was a city hall project, and the guy who was director of development for the city says, "Okay, so when we get done, and when you get done retrofitting City Hall, it's going to work like the Nest thermostat in my home, right?" And I said, "Oh, buddy, man, we got to talk, because what you got now doesn't work at all. But what we get done with isn't going to work at all like the Nest thermostat in your home." But we need to deal with this, because this is going to be people's expectation that things should work like Siri or Alexa or Google Home. We have a shift, a very subtle shift going on and I'm going to talk some more about this, in commercial controls, towards control systems that are going to be all network-based. Control systems today have a little bit of network connection. I talk to owners about, we're going to do a control system and it has 3 network connection points. Almost all of the suppliers now are offering control systems that can be entirely network-based. And I think we're going to quickly make that transition. Boy, how do you design that? How do you engineer it? How do you support it? How do you make that secure? That's a real challenge for somebody like me who's a mechanical engineer. I'm not a network designer. So how do we do that? That's going to be a challenge. And then we have this nasty little issue with cybersecurity, and I'll talk some more about this. But there's a lot of concern going on, and a lot of the work that I've done with the government has been related to this topic of cybersecurity, about what happens when, not if, somebody starts breaking into buildings and either using that as a way to access other systems, or starts using it as a way to take over control of those buildings. And oh, by the way, this is a risk. Almost every control system I work on is all but completely insecure. So this is an issue. And then we have opportunities. We have things we could be doing that we're not doing today. We can be using all of the information from that building, not just for a pretty graphical screen that somebody looks at once a week or once a month or never, but we could be using that information to make decisions. So there's a lot of tools being developed and on the market today for fault detection and analytics. We can start to use this information for operations. We can start to use this so that instead of making a decision about, do I go out and rebuild bearings on that fan every X number of hours, instead looking for the vibration signature and bringing that back and making decisions based on data. And these are some of the opportunities that are in front of us that the technologies enable. So these are good things. Any questions before I move on here? Any comments? This is intended to be somewhat of a discussion, so, or could be. So here's the challenge we've got. So if I go out and I design a building, and I'm that architect and engineering team, I usually design it with a certain level of efficiency. Often we think about this in terms of what we call the energy use index, so many thousand BTUs per square foot. And here in California, we have a unique code called Title 24. The rest of the country, we have something called ASHRAE Standard 90.1, and that says, okay, for a school or a hospital or a commercial office building, you need to design it for this level of efficiency. That's great. So we design it for that level of efficiency, and we stamp those drawings, and we go out and we build that building. And if we don't do the controls right, which we rarely do, if you walk into that building, and I've done this for hundreds of buildings, you can walk into any building, brand new, 5 years old, 10 years old, 20 years old, 30 years old, and you can find things that are not working correctly. I just worked on 2 brand new, state-of-the-art government office buildings, no expense spared. Neither one of them worked right. Why didn't they work right? One reason was that the engineer made a lot of incorrect assumptions. I won't say the word mistakes. The engineer said, I'm going to assume that we're going to have 20 people in that office space over there, and in reality we have 8. So we're ventilating it at the wrong level. Maybe the schedules run longer than they should. Maybe things are supposed to be optimized in a certain way and they aren't. One of the challenges we have is that we have codes today that require a lot of efficiency. They require efficiency through the use of controls and advanced controls. These aren't optional anymore. Almost anywhere in the country, you have to have optimization, static pressure reset, you have to have chiller plant optimization, you have to have demand controlled ventilation. But these rarely get put on projects and they rarely get done right. So most buildings run at a level of efficiency that is subpar. So we have this process, that just drives me crazy, called commissioning. So we'll go in and we'll do that commissioning, and the job of the commissioning agent is to try and make the system work. And ideally we want to drive it back to the point of design, and we get back to that point. Or we'll come back and recommission it, or do continuous commissioning and try and drive it back down there. But we don't really want to do that. I mean, this is like trying to get to that sea-level performance again, right? What we really want to do is have a methodology for optimization, a way that we can be driving that building to better performance, and ideally through data and through grid integration, continuing to improve that performance further and further, to the point where we can make that a high-performance building. And controls are the answer for a lot of this, controls done correctly. Now, I'm a big advocate for what we would call integrated controls. Integrated controls is something as simple as what we call system integration. And often we think of system integration as tying things together. And some of the obvious things we would tie together are things like HVAC and lighting. They both use the same schedule. They both deal with the same occupants. We have a lot of the same sensing in the same spaces. It makes sense to pull those systems together. But back to the concept of that system operator, that system integrator, they're dealing with all of these different systems. So they've got the HVAC, they've got fire alarm, they've got security systems, electrical systems, they may have some video monitoring, they may have lighting. If it's a hospital, they may have medical gas. This airport project I mentioned earlier, we had another 20 different systems, baggage systems, signage systems, elevators, escalators, you name it. All of these are part of the building, and they're part of the building systems. We often think of these things coming together and being integrated, and they come up to some kind of graphical interface, but that's not really the story either. Really, in a facility, we have a whole suite of facility management systems that we have to deal with. We have asset management systems that track what we own and what property we have. We have building management systems that help us do things. We have computerized maintenance management systems that tell us how to process and track work orders and preventative maintenance and other tasks. And all of that comes together into this whole concept of driving back into the business. And it comes back to this concept of what we might call data-driven operations. So using this for things like fault detection and analytics and making good decisions, and then also tying the building back to the grid. Because the bigger challenge isn't just optimizing the building and making it efficient. It's a matter of optimizing the entire system. So one of the challenges we have here, for example, in California, is and I'll go through this in some more detail later, is we have a system with a lot of renewable energy. Isn't that great? Well, it's raining outside today, and we don't have as much renewable energy maybe as we would on a sunny day. But on a sunny summer day here in California, we often have more power in the middle of the day than we know what to do with. I just saw in California, or in Texas right now, there's cases where power is negative in price again because there's too much renewable energy at other times. At other times of the day, every single day, about 5 o'clock in the afternoon, what happens? The sun goes down, everybody goes home and turns on their air conditioner. There's not enough power. So one of the challenges we have is running all of this as an optimized system so that we can use that renewable energy that's good and clean and that we paid for already in the middle of the day, and we can deal with what happens when the system needs to deal with all of a sudden the sun going down or the wind dying off later in the day. Oh, much less like a fire or a hurricane or some other thing that we didn't anticipate. So control systems, as I mentioned, I've done this for a long time. When we first started doing what we call direct digital control, everybody built their own widget. They built their own device. In fact, in the 80s and 90s, there were dozens and dozens and dozens of control manufacturers. Everybody with a dry garage was building something, right? And Ted and Brian, you guys probably remember this. You guys were back in those days. And some of the products worked, some of them didn't, some of them were good, many of them were bad. And if you had the brand A controls system, you had to have the brand A control technician, and you had to have the next piece and part come in from brand A. And if they did a great job, that was wonderful. If they charged a lot of money, that's what you paid. And if they went out of business, you were kind of stuck holding the bag. So one of the things that we did as an industry in the 80s and 90s is we sat down together and we said, let's create an open standard way for these things to talk to each other. And we spent, on the BACnet committee, we spent from, I think, 85 to 95 creating a standard for all of these things to talk to each other. There was similar work that went on in Landmark. This work continues to this day. In fact, this weekend is the ASHRAE meetings. There'll be 4 or 5 days of meetings to continue to enhance this. So today we've moved largely from these proprietary systems, which were on proprietary protocols, largely to open systems. Most new systems today are open. Many older systems have at least partially open protocol. And same thing, all the control systems we built in the 80s and the 90s, we had our own wiring. We had our own way of doing this. We had that twisted pair of wires that connected one controller to the next, and it was this weird little communication. Today, more and more of that is on networks. So we're using a lot of open protocols, and we're using a mix of commercial IT networks and dedicated wiring. So here's a pretty typical, and folks tell me if this is online or not. If I'm off track, let me know. But this is a pretty typical control system. I've got some kind of controller here, like a Johnson NCE or a Tritium Jace or something like that. That's a kind of a system controller and coordinator. And then I've got a controller here for my air handler, and I've got some controllers for my VAV boxes. This one might be in a plant, so it's got some boiler controllers and some chiller controllers. Some of these might be package controls, some of these might be standalone controls. But this is all serial communication, in BACnet, what we call master-slave token passing or twisted pair. This blue wire up here is that Ethernet network, and then maybe I've got a lighting control system, and once again, it's got its own hardwired or dedicated wiring, and it comes back to its own system. Is that a pretty typical building? Yeah? What we see are things moving to just those few pieces on the network, to the ability for everything to be on the network. Why would we want to have all of our controls on the network? Why would we want to do that? Outside of the sarcasm, Bob, one of the reasons we would do it is to get more bandwidth. When we talk about serial communication, it literally is a one-to-one communication. It's the same kind of communication. I see some older folks here. Anybody remember what a modem was? Remember when we used to connect to the network on the internet to the modem? That wasn't that long ago, was it? And things were really slow and clunky. And your modem worked at what, 1,200 or 2,400 or 9,600 baud. Most of our controls are still there. You know, we're at maybe 7,600 baud versus a network where the normal speed is in megabits or gigabits. And the other thing that happens on the network, not only is the network incredibly fast and has incredibly wide bandwidth, but it's also all of our networks today are switched. So as you get that communication, you almost have that one-to-one connection. So speed and bandwidth is one reason. Why else would we want to do this? I'm sorry, what about the wiring?
Subtracting some wiring.
Well, we'd like to subtract some wiring, but does it really, how does a network get wired? What's a typical network wiring diagram look like? Typical network wiring diagram has a wire that goes from a network switch to its point of termination, right? It's what we call star wiring. So the wiring on a network often is it's more consistent, it's more standard, which is great, but often, you know, the way we typically wire a control system is we go from this controller to the controller on the other end of the room, right? Rather than going back to the switch. So in some ways, the network can add more wiring to it. But there's ways around that, and I want to talk about that. Why else would we want to go to the network? Yeah.
Better termination. MSTP is finicky. If it's not termination, you can run into intermittency problems.
You can run into intermittent problems for two reasons, and what are those reasons? So one is termination. What's the other one? What happens if I... Exactly. Because MSTP is daisy chain, so if I break that wire, everything goes down. And that's another big problem with that system. The other big problem is it's just weird. I mean, you know, how many network folks are out there these days? I mean, there's hundreds of thousands or millions of people that know how to do network wiring, and you get network wiring everywhere. How many people really know how to troubleshoot or do an MSTP? Yeah, Bob.
Well, you couldn't meet over here, I mean, we're talking about serial communication right now.
Except for us.
In classes, yeah.
Except for us, we're the exception.
The saddest case in America right now is VRF, whatever they want to call it, any variable refrigerator
Yep.
system that's, infiltrating school systems all over America.
Yep.
The way they communicate isn't IP, it's all serial communication. So when that needs service in the next 5 years and it's dumping a bunch of refrigerant on a bunch of 12-year-old kids, and then they go, oh, supermarket heat treatment is gonna turn into something different. What have you seen out there from a serial perspective on these new manufacturers that are doing what? Pushing serial to cheap.
So I can't talk too much about VRF other than to say that the VRF stuff is very packaged and very proprietary, and they're all kind of doing their own thing.
You guys are too kind to VRF. Really too kind. I hate it much more than that.
I'll tell you a funny, not to digress too much, but I'll tell you a funny story about VRF. So I've done work all over the world, and 20 years ago I was in Australia, and they said, we never saw VRF in Australia, and then about 35 years ago, Daikin came in, and now all we do in Australia is VRF. And you see the same thing all across Asia. Every system is VRF or single zone splits. Same thing across the Middle East, same thing across Europe now. So I heard somebody from Daikin speak a few years ago, and he said, well, here's our vision, and Daikin's the world's largest air conditioning company by far. He says, here's our vision for the world. And he had this chart. He says, here's Japan and Australia and Taiwan, and here's Latin America, here's Europe, and then the next bar was China. Okay, we've conquered all these markets. Here's our last market, it's North America. He said, we're in no hurry, but you're going to see these systems, and they'll get better, hopefully. But they're different systems than we're used to, and I think I think you need to wrap your head around and get comfortable with them, because they're going to be here. And by the way, I live in the Northwest, and people in the Northwest just adore it. So they're like, this is the answer. I'm like, yeah, maybe. Other than there's no ventilation. Anyway. So this is the kind of thing that we're starting to see with new control system architectures. So we're seeing things where we've got this network architecture, this IP connection, and we've got things like our PCs for setup and operations and databases and servers and connections to the cloud. We see things like conventional controls where we're still using MSTP down here. This looks like that old architecture. But look what's new here. Now we're starting to see a number of manufacturers, maybe even most manufacturers, are offering offering IP-connected VAV controllers. How are they doing that? Remember I talked before about one of the challenges with generally when we do a network is we go from this room back to the switch. These folks have done something really clever. They're using a piece of Ethernet communication defined by IEEE called bridge and tree spanning. Anybody here familiar with bridge and tree spanning protocol, BTSP? You want to say anything about it, or you want?
No, it's very effective. It's been around.
Oh, can you pass Robert the mic?
Yeah, sorry.
It's been around for 15 or 20 years. It's well proven in the IT industry as a very reliable protocol. It still uses a daisy chain type technology. You plug two ends of you make a whole loop with your controllers. You plug both ends of the loop into the network switch. The controllers and the switch have a short conversation and decide where's the optimal point to put a virtual break in the network. And if you end up with a real break in the network somewhere, like we often run into with MSTP and it shuts down our network or part of our network, the controllers in the switch renegotiate where the virtual break is and just move it to where the physical break is. So you eliminate that concern unless you actually get two breaks isolating controllers.
Thank you. That's actually a really great explanation of it. So bridge and tree spanning protocol allows you, so what most of the manufacturers are doing is they'll deliver a controller for you that has two Ethernet jacks on it. And in reality, built into that controller is a switch with 3 ports. So the controller is on one port. The other 2 ports, you can plug your laptop into one and you can put the other one on the network, or you can go and start to daisy chain again, which is what we like, but now you put a Cat6 cable between zone to zone, and you go from controller to controller, and then you come back to a special switch, like Robert was saying, that has this bridge tree spanning protocol in it, and you configure it that way. So in normal operation, yeah, it goes out and it communicates with all those in a certain direction, and it can go from direction A or direction B. But when there's a break, it knows how to negotiate that, and it knows how to continue communication. I always tell the story. I worked in a manufacturing facility once where we had the old. Anybody remember the old Ethernet, which was on a coaxial cable? We used to have that thin net, they used to call it, 10^2. About once a day, the gal who worked across the wall from me, she would kick her computer and the jack would fall out and the whole network would go down. So this is the advantage of this bridge tree spanning protocol. The other thing we're starting to see, which is really interesting in lighting, is the use of a network technology called Power over Ethernet. In Power over Ethernet, we can have both the communication and the power go through that same Cat6 cable. And when we do that, there's not very much power that goes over it. There's enough power. It's really designed to run an IP phone or an access point. But they keep modifying the standard and bumping up the power, and our light fixtures keep getting a little bit more efficient. And you're starting to see people introducing light fixtures and switches and other devices that can be powered and communicate from that network cable. So we're starting to see control systems now that are all IP-based. Boy, that introduces some interesting challenges, doesn't it? Some potential benefits, but some real challenges. One of the challenges is going to be how you design that, how you make it work, how you do it effectively, how do you specify that switch with the BTSP thing in it, particularly if you're a mechanical engineer and you don't know what any of those words mean. The other issue we have here is cybersecurity. It's really interesting. A few years ago, people were really focused on this issue. A few years ago, does anybody remember what happened at Target? Does anybody really know what happened at Target?
The contractor was given access to the
Exactly,
billing.
exactly. So the story came out in the press that somebody broke in through the controls and they lost all the reality. In order for a contractor in Pittsburgh to get their work orders, they were going to a server. Once you got to the server within that system, you got access to the entire network. Insane, I still have people to this day that say, oh, the Target is the biggest controls-related thing. Not exactly, Read the data, But anyway, control systems are not secure today. If you get on a control system today and you get valid access and you go out on the wire and you do a backnet whois, you'll get back another backnet command called IM, and all the devices will identify themselves, and then you can go and read and write anything that will validly accept a read or write command. They're not terribly secure. So that there is the potential of two things that are really dangerous here. One is that somebody could easily get into buildings and take over control. And my reaction to that in general is, okay, so what? I can think of some scenarios and some places where that would be really, really, really bad. But in general, the reaction is that if somebody broke into this room and overrode it, what would they do? They'd make it uncomfortable. It's already uncomfortable in here. Maybe they would. Maybe they'd lull us into comfort. There's very few real stories, but there will be eventually. The risk is there. The bigger risk is that they're going to come in through what we do with control systems, and they're going to get into something else. They're going to use this for what we call vectoring. They're going to use it as a method to get in to find information that's in databases or in financial information. There was a story that's like all of these stories, unsubstantiated, about somebody that came in through an IoT device in a casino and got access to a database. That's the real risk, is coming in and getting to other things and using this as an access point. So how do you get around? How do we provide cybersecurity? Well, because we came out of this world from a dedicated world, we never thought about it. All our systems are obscure. Who cares about BACnet? I mean, that's such a weird thing. But now you can go and download tools from the internet. You can be doing BACnet sniffing and analytics very easily. It's not as obscure and weird as it used to be. So we need more expertise to get around this, which is really difficult. I think this starts with best practices, and almost every controls manufacturer, has a best practice white paper out, and most of them are pretty good. Best practices are things like using VLANs, virtual LANs. They're using VPNs. They're making sure that you don't leave your default passwords in, which everybody does, and managing your network right. That is a good start. Did you want to have something you wanted to add?
I
Yeah.
do have a story that's very similar.
And ties right in with the best practices and specifically the use of virtual LANs. A virtual LAN, by the way, is a separation within a network, like walling off a portion of your network so that only things on that portion have access to that data. It can be very effective for reducing general broadcast traffic on a network, and it also is immensely useful from a security standpoint. You can wall off your point of sale systems, for example, so that the only thing that can communicate with the point of sale system is the point of sale system, so you don't have breaches like the Target breach. But one of the ones that I've run into very recently is there is a chain of restaurants that I'm sure all of you have heard of, Panera. Okay? Panera has a corporate account with one of the controls manufacturers, not one of the big manufacturers, but still a significant one. And they have a new type of control system that one of the ways you can program it on initial installation is using an app on your phone. I just so happen to have this app, and it's really funny because every time I walk into a Panera and connect to their wireless network, my app pops up and says, "Hey, do you want to configure this system?" A
Default information again.
default information, not using best practices, not using VLANs to separate it off.
I like the example. I told you I've been playing with some of the IoT things at home. And the IoT stuff, you know, if you want to set up a smart internet-enabled light switch in your home, you know, you plug in and you power it up and you walk up to it with your phone and you connect your phone and it acts like a wireless ID point. You know, that function is never disabled. You can walk up to anybody's device with your phone and redo it. The only thing that protects that is the proximity. You've got to be within a few feet of it. So yeah, all of these things. And the same thing, you know, there's a lot of systems now that have a Bluetooth interface in order to program it and set it up. You need to lock that stuff out. So there's a whole series of best practices that are a big deal. There are some bigger solutions that are coming on board. I mentioned that the BACnet committee, which had met for 10 years and created the standard, the folks that are dedicated to this committee continue to meet 4 times a year for many days on end. One of the things that they're working on, and in fact they're just finishing this up, is a revision to BACnet called BACnet Secure Communications, and I'll leave this white paper here, and Peter, maybe you can distribute it for anybody that's interested. This is something that the committee has finished work on. It's been out for review. I believe it's just in the process of being approved as part of the standard at this point. But it's a method to take BACnet communications and have it go not using the way BACnet normally works over a network, and I don't, you know, this gets way into the weeds. Right now, BACnet uses its own communications over a network. It has, in networking terms, it's what they call a datagram. So when we go into an IP network, we don't use TCP/IP. We use something called User Datagram Protocol, which is UDP. What this new method uses is just BACnet uses just straight stick plain network communication. It's no longer weird, and it's then able to use, you know, when you connect and you get that little lock on your browser, that's what's called, used to be called SSL, and now it's called TLS. It uses TLS, which is the industry method of encrypting and communication. So it's using straight stick, regular, old, IT acceptable communications. It's a big change for BACnet. Many of the vendors are starting to build products that will follow the standard. They've been working in the background kind of to build those products out. I think you're going to see a lot of products starting to come on the market that use this, but it's not a trivial change. In order to have a controller use this, you need to have security keys, and because you're not on the internet, you have to manage your own keys. It's not, it'll be interesting to see how the vendors support it, but it's not trivial. Mark, do you have something to add?
Who's going to, I mean, Basically, my big problem is with the IT folks at my school, and I'm sure everybody has similar experiences. We basically carved out our own network between myself and the engineering department, separate from the college network, to do our lab stuff on. One of our head IT guys in the college, his name for it is HackNet. You know, and that I found that to be very common in the IT world. They don't understand. They believe the target story. You know, and they're so fearful of the way that BACnet is done. And their few experiences with controls companies have not led them to change these beliefs. They've only, you know, reinforced them.
So that's the $1 million question. Thank you. Thank you for forming that succinctly. So the question is, who's going to do this? Because here's the challenge we have. We have controls that are designed by HVAC engineers, and we don't know networking. We have things that are installed by contractors who have a little understanding of networking, but not much. We have IT people who have a deep understanding of network, but don't understand controls. And then we have cyber people who don't understand any of that, and they understand stuff that we'll never understand. So a lot of people advocate teaming. A lot of people are starting to do crossover. I know a lot of institutional, like college campuses and things, where they brought IT people into their facilities group just to start to get that crossover. But it is really a challenge because there aren't a lot of people that can speak the different languages and live the different worlds. The changes to BACnet will help because that means we have to do less explaining about what we did that was weird. And I've had this discussion 100 times, and you've probably had it 100 times. We probably all have. Why does BACnet do it this way? The IT people are like, you guys got rocks in your heads? Why didn't you do things? And the answer is, do you know the answer to this, by the way? The answer is we built BACnet before IP existed. That's the short answer. We developed BACnet. We started working on BACnet in 1985 when the predominant standard was from a predominant networking standard was from a company called Novell that no longer exists anymore. The internet protocol was something being used in colleges and research institutes. So we started this before IP existed. And we've been constantly modifying BACnet to work with it. But this new version hopefully will work better. But this is something that you're going to see 3 years, 5 years down the line before there's really a lot of product and solutions out here. Now I've lost my remote. This is not good. So BACnet Secure Communications is going to help. Keep this in the back of your mind. It's something that's coming. There's a lot of dedicated security appliances, a lot of vendors that are coming out with solutions that will help with this. And then I think we're going to need a lot of work on improved network design and management. It's not going to be... I know I was at an industry conference, and one of the sessions was a system integrator here in the Bay Area saying, you know, the answer to this is that we just need to split off our networks. They need to be completely isolated. And I said, that's fine, except for the fact that that diagram I showed you before where you want all that information, that's what we need. So it's not as simple as saying that. So it is complicated, and there's not an easy answer here. And this is something you need to be thinking about for your programs, about how you're going to deal with network design and management and security and communications and reliability. So that's my takeaway on that. The other thing that's really, really important on control systems, the reason we put in control systems is they're supposed to make the building comfortable and efficient, right? That's why we did it. So we need to have controls so that our systems are optimized for maximum efficiency. That means that we don't need to be pumping any more water or moving any more air than we need to be doing. It means that we don't run things any longer than they need to be running. So when something isn't needed to be for occupancy, it shouldn't be there. It means it should be ventilated to the level that keeps everybody healthy and safe, and no more and no less. It needs to be highly usable so that people can figure this out. These systems need to be data-driven. They need to be connected to business, enterprise, and utilities. And they need to do the magical solution of being easy to use and easy to install, but highly sophisticated. Isn't that impossible?
Every client wants that, right?
You know, every client wants that. And you think, oh my gosh, we could never do that. And then you turn around and you look at something like a Tesla or a Prius, and you say, they did it. And did anybody take the class on how to drive a Prius? Anybody had that course? I did. First time I ever rented one, I was at the San Francisco airport. The guy says, get in the car, put your foot on the brake, push the button. I said, okay. That was the class, you know. Other than that, it drives like a car, right? I don't know what it's doing in the background. I mean, it's got the gas engine going, it's got the electric engine going, it's charging the battery. If you look at the charts and graphs, it's doing 10 million things in the background. That's what we need to do with buildings. We need to have that level of sophistication, but we're not there yet today. So ideas of optimized controls, all these things are in codes and standards today. It's things like using outside air to cool the building whenever that's possible rather than using mechanical cooling. I'm giving Peter a hard time because the cooling tower is here running full blast and it's 50 degrees outside and school's closed. You know, how does that work? We need to manage ventilation using demand-controlled ventilation, looking at CO2 levels, looking at occupancy levels so that we ventilate correctly. We need to optimize those pumps and fans so that we get as low we need to ride the edge of that fan curve so we get as little pressure and as little air as we need to provide exactly what's needed for comfort. We need to optimize the way the chiller plants work. We have to use lighting efficiently. We have to use those systems required together. And all of this, hey, guess what? All of this is in the code already. You build a building to ASHRAE standard 90.1, 2010, or 2013, or 2016, or California Title 24. Every single one of these things is required. How often are they done? How often are they done right? Almost never. So all of this is required by code, which means that all should be being done, and it doesn't work. Why doesn't it work? Why aren't we effectively delivering highly optimized buildings and highly advanced control systems today? Lack of talent? Lack of talent where? Everywhere? Yes, that's the short answer. Lack of talent with...
Everywhere from the inspection down to the...
I would start with the design engineer, the inspector, the contractor, the operator. Yeah, we have a lack of talent, we have a lack of understanding, we may even have a lack of interest.
If you look
Mark?
at our process, it's amazing anything gets done at all.
Exactly. We have a process. That process I described before with the silos that's really difficult. So there are some things underway to help fix this. So this is the good news. I'm not here just to complain today. I'm here with some solutions. So we have process challenges. Mark, you hit I always say when there's a slide to support it, it was a good answer. So it starts with the problems we have with design. Most mechanical engineers are responsible for writing the control sequence and the controls design. I have trained hundreds and hundreds of engineers in controls, and generally they could care less. It's not generally an area of great interest to them. The way that this used to work is, by the way, is that the controls design used to be done by the contractor, and then now it's the engineer's responsibility. And the engineers are like, whatever. I got one guy in my office that knows something about it, maybe, sort of. So we have an issue. Yeah.
As a consulting engineer,
Yeah?
a few people here that come out of that background, and I'd say that it really is a firm by firm decision. It's a firm by firm decision. Some firms have an interest in doing controls. In our shop, which was about a 40-person shop, only the partners and the associates would write the control specs because most people didn't know. You need a lot of experience to understand. And I think and on the other hand, I know there are some companies that would put together a set of control sequences that was so generic that you had to check the drawings to decide how many chillers were to be controlled because they had, if you have one chiller, if you have two chillers, if you have three chillers. So they didn't put, it was all just boilerplate. So I think it is a function of talent, and if the talent is interested in doing the job.
You're absolutely correct. It is very variable, and it is firm by firm. There are some firms, and I do a lot of this work. I like to think I'm good at it. There are some people that are really good at this. Steve Taylor here in the Bay Area is excellent, one of the best people in the country and in the world in doing this. But by and large, there's not enough focus, not enough attention, not enough talent. I'm glad to hear that you had some senior principals that did it, but it's not something that our younger folks know, and it's not something that's well enough understood. So we have issues here with the ability of the designer. They're challenged often doing designs, doing sequences. Designing integration is even more difficult. And I do a lot of integrated design, and the only way it works, which is I'm not advocating as a process, is we have to break the process. You know, we have to say, what is it you're using for fire alarm to the fire alarm guy? And what is it you're using for lighting? And how are we going to connect these together? And how do we get that meter to talk to this? It doesn't happen easily. We have, unfortunately, serious issues on contractor quality control. When I do control projects, I always pre-qualify my contractors. I find the best contractor in the market. I find the person that's going to give me the best price, and those are the only people I work with. And every single time they screw up. And it's not because they mean to. They're good guys. I hired the best guys. So I'll tell you a typical discussion. And this is where's the guy from Greenville? It's a Greenville discussion, so it doesn't need to get repeated. I did a project in Greenville where it's really warm, beautiful area, but it's a February day, and it's cold in the morning, and the building won't warm up. And the guy calls me up, and he says, Paul, you know, you screwed up. The building didn't warm up this morning. And I said, well, okay, let's see what happened. So the boiler comes on, the air handler comes on, and the damper is fully open in a normal occupied mode. So I go back, I said, I could have sworn in my sequence I wrote that when you do morning warm-up, the outdoor air damper should be closed. I could have sworn. I go back in the sequence, oh yeah, sure enough, here it is. In morning warm-up, outdoor air damper shall be closed. Call up the contractor and said, doesn't it say in the sequence that should be closed? And he's like, oh yeah, you're right, it does. I'll fix it. This is my life, right? You know? Yeah, Mark.
I can tell you, I was on the user side for a long time. I've been in industry as the owner's rep, in charge of maintenance operations. And to this day, I know very few mechanics and building operators that even understand what optimum start is, morning warm up. They put the building in occupied at 6 in the morning because people are going to be in by 8.
That's absolutely correct. And I always like to tell the story. One of the first efficiency projects I did was a big hospital. And this hospital, everything ran 24 hours a day, 7 days a week, except when they designed it, there was one time clock in one zone that was supposed to shut down, which was the lobby, because the lobby was closed from 9 in the morning or 9 at night till 6 in the morning. And of course, like all buildings, the trippers were removed from the time clock. And I went back to the building engineer. I said, Matt, explain to me why the lobby runs 24 hours a day. He said, oh, yeah, sure, I can tell you why that is. It's no problem. He says, one day, I come into work, the hospital administrator, and he says, Matt, why is it so cold in that lobby this morning? He said, I fixed it. I said, oh, yeah, you did. But we have serious issues with the quality control from contractors. They may or may not, we may or may not write the right sequence. They may or may not read my sequence. They may or may not implement what we need. Yeah.
I just want to
Yeah.
mention that. I think one of the things that happens in a control company is that you have a disconnect between the people who installed the system and the people who engineered the system. The system engineers, the ones who put the control diagrams, specified the parts, who've interpreted the sequence of operation, they're not necessarily following up the project. It's kind of handed off to people who do the install, who may not know why the sequence was written the way it was. It happens all the time. You come to a job, how come this sequence isn't working? This is the one we do. This is the way we do offices all the time. You do it at the museum.
That's absolutely correct. Yeah. I wrote the sequence for a specific reason, and you should have read what I wrote. We have serious issues with the contractors with programming installation. We have systems commissioning, by the way, is our industry solution to fix this. So when I come in and I commission the project, my job now is to make sure the contractor did it right. If the contractor done it right, I could be not doing that. We have some issues still with product, not as much as with process, but there's some minor issues. Things could be faster. They could integrate easier. We could see some more innovation in products. That would be cool. And then we have challenges with operators. We don't have the capabilities and training, and that's why Best Center is so vitally important. There are some solutions coming. This is exciting. So does everybody here know who ASHRAE is before I go into this? ASHRAE, American Society of Heating, Refrigerating, and Air Conditioning Engineers. ASHRAE is our engineering organization. I'm going to talk about two different projects going on in ASHRAE, Guideline 36 and Proposed Standard 223, and I'll go into those in some more details. And then I'm going to talk about some of the things that the Department of Energy is doing in terms of advanced controls. And I'll go into each of these in some more details. So one of the things that ASHRAE decided a few years ago is we should be able to have some standard high-performance sequences that everybody could use. Those of us who are really, really, really old remember back in the day when we had unit ventilators in classrooms. You remember this, yeah. And there was an ASHRAE sequence 1, 2, 3, 4. And all we did is said, provide ASHRAE sequence 2. And we didn't know what it was, but we said that's what goes in our spec. And life was good, right? They didn't work very well, but this is what we said. So Guideline 36 is a really interesting guideline because it's a group of really smart people that sat down together. Is Jay coming this week?
He was here yesterday.
He was here yesterday. So Jay Santos is part of that committee. Steve Taylor from Taylor Engineering is part of it. Mark Heidemann, who had been with Taylor and is currently working for Google, is the chair of it. Bunch of smart folks that sit down, and they have figured out what they think is a really good sequence, starting with air handlers. So they did multi-zone and single-zone air handlers. And then they went to ASHRAE and said, okay, we want to have an ASHRAE research project and prove that this really is the best way to do it. So they did both what they thought was the best way to do it, and then they did the research project to prove it was the best way to do it, and they published that as a guideline. So they published the first version of it, which is air handling systems, so it's VV boxes, multi-zone air handlers, single-zone air handlers. They're working on chiller plants now, and then they'll come back and do chill beams and other things.
Mike died yet?
I'm sorry?
Either your mic died or it's too far away.
Yeah, it's red light again. I'll keep
I
talking.
think that heat sensitive button also shuts it off if you can't.
I'll keep talking loud and I'll let you change it up. Okay. So Guideline 36 is the industry's effort to define the best way to do this, backed up by research. So it's out. Has anybody seen it?
Yes.
Has anybody read it?
Yes.
And what did you think?
Complicated, not sustainable.
You can't figure it out, can you?
Yes.
I can't figure it out.
Yeah.
I'm in the middle of this stuff. And the challenge that it has, and I chaired and helped write Guideline 13, which is the standard guideline on control specification. It's the same problem. As an ASHRAE document, it's not a sequence of operation. It is a primer on how to write the best sequence of operation. So you kind of have to sift and sort between it, which is a challenge. But the sequence, by the way, by and large is good. There's Steve Taylor sequences, frankly. This is the dirty secret. The challenge I have with 36 is when I do an air handler, I do everything that's in 36, and then I've got to do everything else. So what do I do for emergency shutdown? What do I do for fire? What do I do for pressurization? What do I do for freeze protection? None of those things are in 36. So I can't stop at 36. And then if I got something weird, which almost every building has something weird, you got to go beyond that. But it's a good starting point. It's good work. The committee, I think, is not totally unified, but I think it's good basic effort by industry, and it's something everybody should be aware of. But that's my comment. Strong work, but still a challenge to implement. I had a building I wanted to use with 36. I couldn't figure it out. I had the same problem.
Well, not only that, but if you can't figure it out from the engineering perspective, how is the operator going to understand what it's supposed to be doing? And I can tell you that the first reaction when they don't know is to hit that override button.
And I'll tell you, Jay's comment on it is there are buildings it would work well in, and there's a lot of buildings where it's not the right thing for the operator. It's just too complicated.
I think that's Jay's critique of Steve Taylor.
Yes, I think that I think that's the difference in perspective between Steve and Jay of the world. Yes.
Yeah.
Yeah, I think that's absolutely right. There's another effort going on in ASHRAE called Standard 223 that is, let me just back up for a second. So one of the problems we have with control systems, and you've all worked with control systems, is you go and look at something in a control system. If you look at the graphical user interface, you can see a graphic of a floor plan of a building, and there's a temperature, and the temperature you assume is the set point of the temperature for that room, and you can kind of sort of figure out what's going on. But if you go in and look at the control system, and you look at something and it says it's analog input 8, or it's analog input for room 223, and it says it's 70 degrees, it says it's 70 rather, is it in degrees, is it in Fahrenheit, is it in Celsius, is that the set point, is it the temperature, is 70 a good value, is 70 a bad value, how many people are supposed to be in that room, how's the room supposed to be used, is it occupied or not? all of that information that goes around a piece of data is what we call semantic knowledge. It's the next depth of the data, right? So everything that goes around that is that semantic information, and because we don't have that semantic knowledge and it doesn't have that context, it doesn't have that tagging in it. So there's a couple of industry efforts that have started up kind of in an ad hoc way to try and, he left with it, that's not a good sign. To try and define that. One of them is called Project Haystack. Anybody familiar with this? Project Haystack was started by the folks, a couple of different folks, but mainly from the folks from a company called Sky Foundry, as a way to kind of just get people together and start setting up some ways to identify data, and just an ad hoc way to do it. Another thing was done with something called Project Brick, which was done out of UC Berkeley. What ASHRAE has done is ASHRAE, through the BACnet committee, has stepped in. They're working jointly with Haystack and Brick to create a standard, an ANSI standard, for semantic information. So this is work that's going on right now. I think this will be really important work, that we'll have standard ways to define this. One of the challenges they have is, you know, words mean different things. So one example is, you'll see people use the word area. What does that word mean? Does area refer to the dimensions of something and its volume, or does area refer to a location? So they're trying to define that semantic thesaurus, that library, how you define things. So this is another really important industry effort that's going on within ASHRAE. Another project is one that I'm involved with. This is a project that's being funded by the Department of Energy and the California Energy Commission. It's a project taking place at Lawrence Berkeley National Lab. And you guys are going to Lawrence Berkeley tomorrow. You may or may not hear about this project. But this is a project called Open Building Controls. And this is a project that picks up where 36 ends. It is a way to do three different things. The first thing it does is it gives engineers a tool set where they can take a sequence and try it out and play with it and see how efficient it is. So the challenge I have is, I think my sequence is great, but I don't know. I mean, so what this does is it allows you to create a sequence and say, I want to try doing it this way. It uses a program from the Department of Energy called Open Studio. You can very quickly put together just an outline of your building, try option A against option B against option C, and see which one's more efficient. So it's a tool set for engineers. When you get done creating this sequence, it spits out a machine-readable file that we call the control description language file, the CDL file. That file is different than the, does anybody know what we usually do sequences in? We use it in this verbose format. We say air handler 1, during morning warm-up, the unit shall close the outdoor air damper, shall open the heating valve, shall run at full speed until 3 zones are satisfied, or whatever. The CDL, and so what we do is we write this verbose description that may or may not be right. That goes to that advanced engineer in the control contractor's office who might revise that or might just cut and paste it and put it in the specs. That then goes to some junior level person who writes the program. And then they write something in the control programming language that goes into that automated logic or Honeywell or Johnson or whoever's controller it is. Or they pick their standard program and dump that in and don't use yours or whatever it is they do. The controls description language is a machine-readable file. It is the controls program. It comes from the engineer. You can now take that program, you can run it through a translator, and it can come out in, for example, automated logic icon programming language, and you pop that in the controller. So this whole interpretation and decision-making and issue about translating and interpreting and deciding goes away. So now when you go to commission it, you've got the program the engineer created in there, and you can start with things like Guideline 36, because now we have this industry best effort. And then the final piece it will have is something where you can actually plug a tool in and it will actually document the sequences that are implemented in a control system.
So is it some kind of a text reader? The program is some kind of a text reader that translates?
No, it actually creates control programming language.
Like a compiler?
Not like a compiler. Like generally, so we're still working on the user interface, and then there's some magic that has to occur.
The programming commands.
What the way I think it will work in the end is as an engineer, you'll go through and use a tool and say, if you ever use the tool, it'll be like Control Spec Builder. You'll say, here's how I want to do fan control, here's how I want to do hot water control, here's how I want to do this, here's how I want to do that, and you'll pick the things you want off of it, or you'll go in and say, I want guideline 36, and it will pull that out of a library.
It could be just as scary if the people, you know. the
Garbage,
certain
it's garbage in, garbage out still.
Yeah,
Exactly. You also could say, and if you've done this before, Don, you've done this. You know, I rarely start from scratch on a sequence. I usually start with something I did before and modify it. I could start with my library. So your firm could have a library of things that they've done before, and you can pull it in and start modifying it. But that's the concept of this project. And in simulation, you know, we have shown that this ends up in energy use that is 20 to 30% less than standard control. So it's a significant thing. This is going to go together hand in hand with what ASHRAE is doing with Guideline 36. In fact, the Guideline 36 people are very involved with this project. So this is a really interesting project. This is a close cooperation, shows potential for 30% efficiency improvement. We started work in 2016. We've finished the modeling tools. We've done case studies. We're doing a lot of, in fact, one of the reasons I'm out here this week and next week in Atlanta, we're starting to figure out what the next pieces and next steps are for how we get industry involved in this project. There's a whole series of other projects that the Department of Energy is doing. I have one I was involved with where we were using artificial intelligence and machine learning. Actually, you know, the traditional way we do optimization is by something called trim and response. We introduce a little bit of an error and we see how the system responds and we keep bumping it back and forth. The end result of that process that we use in most control systems is that it's better than running at a constant set point, but it's not optimal. You can get to the point where you can run at the optimum point of the fan curve by using some co-simulation and machine learning. In simulation, once again, we're seeing about another 15 or 20% efficiency improvement over what we see in Guideline 36. So once again, this is new technology, things that are, you know, this is not next year, this is 5 years out, but this is really promising. The other program, a lot that's going on is in fault detection and diagnostic. There's multiple projects and programs here. I just met with the person in charge of this at the lab yesterday, and she said, yeah, and this blew me away. She said, we just finished a database of 300 to 400 million square feet of space that have fault detection and diagnostic installed, and we've documented what it's all cost and what all the benefits are. I thought, wow, I didn't know that. That's really valuable information. So there's some really interesting things going on in this space. Bob?
So, one of the things I got a problem with.
Yeah. Hang on, I'll let you speak into my mic.
Got a bob.
So you get a lot of energy in, energy out, people getting taught at whatever engineering program they go to. You know, back in the 1800s, they used to make people, engineers at Boston Tech had to go to a 4-year apprenticeship to learn how it worked when you actually installed it in the field. And that school today is called MIT. It's interesting when you have 80 engineers in a room, all learning about chill water systems, different parts, kind of the same region, and all of them are designing crap differently. And there's no standard there either. And then you throw controls into the mix on top of the mechanical, and then sequence of operations, and then people that only understand energy, and they start torching people's, you know, plant and equipment, and nobody's even getting sued for it. So, I mean, is there going to be a new law firm that starts up and starts suing controls contractors? We could make $1 million. The guy said we could be rich, right? For all the equipment destroyed across America, for people not going in and understanding the full spectrum of systems. And until that program, maybe another division of engineering starts and carries across the country, we're going to keep hitting the same problem of a bunch of know-it-alls that don't know anything. So.
Thank you. I can't disagree with you. As an engineer, I can't disagree with you. And I know that there were some criticisms before, and we don't need to get into this today about VRF. VRF, because VRF systems don't get engineered other than by the manufacturer, they tend to work better. because we can't fix them.
But let me give you an example of a Lee building, which was built, where they used the VRF and geothermal system. And they put drives on the pumps to
Right.
run the system.
Yep.
But because they couldn't talk to the VRF system, they couldn't anticipate load changes. The drives couldn't react fast enough, and the condensers were always tripping out. And so what ended up happening, they jacked the pumps into 100%.
Sure.
Let it
They
run
fixed
up
the
the
problem.
curve, and keep the system running.
And back to Bob's comment. So, as engineers, we get sued all the time.
Go on.
We get sued over stuff, and this is your question yesterday, Bob, about did an engineer ever size a pump right? We don't get sued when we overdo things. We get sued when we underdo things. So as a result, and this is just the nature of the business, we're very conservative and we're very cautious. We tend to oversize things. We tend to overventilate things.
Double it, man.
Over velocity, destroying pipe.
But that's because that way, you know, yeah.
I would I'd like to make one
Yeah.
comment.
Yeah.
I think one of the issues, and again, when you're really close to a particular thing, if you're operating a chilled water plant, that's what you do every day, and you really understand a chilled water plant. On the engineering side, the mechanical engineering design profession has gotten so incredibly broad because of life safety. For instance, when you do a job, I would say about 40% of what you do on that job is related to life safety. That's something that operators don't necessarily see. So there's a tremendous, the profession, and I'm in the profession 40 years, I've seen the profession triple, quadruple in terms of the amount of information that we dump on the mechanical engineer. Really, you need to have experts in every field, and nobody's willing to pay for it.
Right, that's exactly right. Yeah, and the fees don't go up at all. Okay, let me kind of move on here. Last thing I want to talk about in closing here is a little bit about building to grid integration. This is kind of the last piece. This is kind of the next step in building controls. This is beyond simple demand response or getting a call from Ehrlich saying tomorrow's a high demand day. This is the challenge here is to find that balance between the comfort, safety, efficiency, and demand response, so we can do what we call integrated demand side management. So we can make that building work still efficiently and comfortably, but in concert with the grid. There's a lot of industry work underway here to create things like this energy services interface, but there's a lot of challenges here. So here's the basic challenge. If you think about this from a utility side, on the supply side, they've got these baseload plants. These are their big coal plants and their big nuke plants. They run flat out all the time. Life is great. Then they have what they call load following generation. These are the gas peaking plants, and those are ones they can turn on and off relatively easily as they need. They've got a little bit of storage, some pumped hydro, here in California, some battery, and then they've got this whole challenge with their renewables. And their renewables, when the wind blows, they get wind. When the sun shines, they get solar. And when it doesn't, they don't. That's how that works. That's the supply side. So if you're a utility, if you're PJM or your BPA or your PG&E, this is your life, right? This is what you create. And then I had a friend once who said, you know, in the utility world, if the utility world worked like the airlines, the customer's expectation is every time you wanted to fly someplace, there would be a plane waiting at the gate, waiting to take you there. So the utility world, they don't know what the demand side is going to use, but they're there to provide it. So on the demand side, we have our built-in demand, how much power our building or our industry or whatever uses. Energy efficiency can bring that up or down. And then we have the ability to shift things a little bit, what we call interruptible load through demand response and some time-based demand response. We may have some local storage and or batteries, but that's the equation. That's what you got to balance, right? At the end of the day, all of this has to equal and in real time, by the way. There's no flexibility here. So the challenge we have is this thing that they call the duck curve, and this is from CalISO. This is the current world. Life is pretty good. So a typical average day here, this is how much power is created in California. Or I'm sorry, this is the load that exists in California, net of generation. And it kind of comes up and it's relatively flat during the day. There's a big peak here in the evening when everybody comes home, and this nasty thing that occurs in the afternoon. The expectation, and this is already occurring in areas like Hawaii and is starting to occur in California, is as more renewables come on board, we actually have too much capacity in the middle of the day, and we have which actually isn't a problem because the way all of our solar works, if there's too much capacity, what happens if there's too much solar online? Anybody know how solar systems work?
Too much energy on the line burns the wire. Let's go back to basics.
No, it's not producing. I mean,
Exactly. Exactly. The way solar works, under the safety standards, is that all your solar inverters look at the power coming in, they look at the voltage, they look at the frequency, and they match that. If the voltage or frequency is out of range, if the voltage is too high or the frequency is out of whack, the inverter shuts down. So if you have 3 houses on a circuit and it's a really, really sunny day and you've got too much capacity, you don't put 140 volts into the line, you balance it out. So if you get too much power, we just don't generate as a safety measure. In California, there actually is a new standard coming in where they're going to, oh, you got another one? Thank you. Can I keep using this one? Sure. Okay. In California, there's a new standard coming in where they're going to modify that frequency a little bit as well. But this is the challenge, we've got to balance that curve out, and the renewables make that a little bit of a challenge, particularly when we have a lot of renewable integration. Yeah.
Paul, could you go back to the previous slide for a second?
Yeah.
And, for example, the Northwest, which has a lot of hydro,
Mm-hmm.
and they have wind. What kind of what are we, Germany has a lot of wind in the north and production in the south. Denmark has gone to almost 100% renewables. How are they doing it? Or what are some of the...
How are the Europeans doing it, or how do we do it in the Northwest?
Both.
So here's the challenge, is you need a system. Ideally, you need a system like Spain has. Spain has a tremendous amount of wind, and they have a tremendous amount of gas generation. So they have 2 identical systems. They have a big wind system and a big gas system. And normally, the wind is blowing, and they run all on wind, but when the wind dies down, they have the gas system. The problem with that is it's not economically viable. It's horrendously expensive. They happen to have built the gas system, then they built the wind system, and now they have all these financial problems. But ideally, if we could integrate this more intelligently, and we didn't have to build 2 identical systems, and we could use more storage, or we could use more building flexibility, we could build a much, much more efficient solution than 2 identical systems where one has 10% utilization and one has 90% utilization. In the Pacific Northwest, we struggle because we do have all this hydro. The hydro has got some controversy to it because of the fish issues, and we try and balance between all those. But what we do in most parts of the country is it's a market-based system. So when you go to a utility like PJM, for example, in the Northeast, they do an auction, they buy the cheapest power first, and they buy the most expensive power last, and there's generally is a premium for renewables. But the fairness issue on this is a big issue, and in order to get a lot of renewables going, we went to this great system called net metering. It got a lot of people to invest in renewables. Turns out that isn't fair for the poor ratepayer. So it's everything's hard to balance out. But ideally, we have a very flexible system so that if there's if the renewable capacity moves around, or worse, we get a forest fire and we need to move around where the power is going, or a hurricane or a flood, or God forbid an attack or a terrorist event or a cyber event, we have more and more flexibility and control, and that's ideally what we want to achieve here. So how do you do this? You got to turn something off in your building. I mean, we have as much as we need to be running in the building. So we have things like energy efficiency, like scheduling and sequencing and variable capacity that raises or lowers the amount of power we use. That's pretty straightforward. We have things we can shift. We could take that building in the middle of the day when we have a lot of renewable power that we need to use up. We could cool it down a couple degrees and let it heat up later. So we could pre-cool or preheat. We can just defer. We can say, it's 4 o'clock in the afternoon and we're really short on capacity. We're just going to let the temperature drift up a couple degrees. That's valid. We could do something really smart, like we could take wind power when it's abundantly available and dirt cheap, and use it to freeze ice and use that to cool the building during the day. That's a really cool solution, thermal storage. There's a fantastic concept that we're working on in the Northwest right now to use heat pump water heaters with a built-in electronic mixing valve and command those so that we could take water heaters in the home and heat hot water up to 140 degrees, and then mix it down to 120 for safety, and use that as a bank for thermal storage. And then that way, you'd heat all your water in the middle of the day when we have a lot of hydro and wind, and you'd use it in the evenings or in the morning when you need hot water. So that's a pretty cool solution. And we can shed things. We can adjust set points. We can dim the lights down. I had a client I worked with in San Jose. They said on a high demand day for Cal ISO, we shut all of our lights off and we send all of our employees home. If it's that bad, we'll do that. So that's a radical strategy, but that is a strategy. But there's a lot of things that you can turn on and off. This is a whole list of building loads for a research project we did. Everything from test lab equipments, plug loads, signage, laundry, chilled water plants, how big they are, what you can control how. These are all options. These are all things we can control. I have a similar list to this for residential loads. There is nobody in this country that wants you to turn their TV set off because we're in a high demand situation. But there's almost nobody that would object to defrosting their freezer at a time other than it defrosts right now, because nobody knows when that is right now. So some things people are really flexible with, some things are completely unacceptable. What? Yeah. So this is the kind of concept of an integrated system that would accommodate this. So up at the top, you've got a demand response server from the grid or the utility. You've got some communication, and then it can come back and talk to these systems. This is a project that we did in Ohio probably 5 or 6 years ago to test this out. This is a building. You can't see it real clearly, but it's 2 office towers. I think they're about 50,000 square feet each. Each of the towers had its own mechanical system. It's a water source heat pump system. So each tower had, up on the penthouse, had cooling towers and boilers and pumps, and then a couple hundred heat pumps in each building. The one building had been retrofitted already, and we didn't touch that. The other one we did a brand new control system in energy efficiency and this demand response test. I'm not a big advocate of wireless, but this is a project we did using all wireless communication. Worked really well using a product from Viconics. And because this was a science project, we installed a ton of sub-metering throughout the building. And so we tied in all of the water source heat pumps. So we had the ability to adjust their set point. We tied in our sub-meters. We tied in the ability to control some electric water heaters and some electric water coolers, which weren't worth the price of doing. And we did this to test this out, how this would work. So we came in on the hottest week of the year. The property manager described herself as a mother hen. She said, my main concern is my tenants. You do anything to mess with my tenants, I will get you. So she was kind of watching over our shoulder to make sure the tenants weren't unhappy. And we did a whole series of tests. So we did 4 levels of control. In level 1, we just controlled the set point by 1 degree. Level 2, 3, and 4, we kept moving that set point further and further and further apart and to see exactly what would happen. And this was a pretty typical response. We would come in and signal this. This didn't quite come out right, but this is the building demand load dropped by about 30%, and then after that 2-hour test went back up to where it was before. And this, once again, didn't seem to work very well. But this is level 1, 2, 3, 4. We didn't get any complaints from the tenants until we got to level 4. And as I said, we had 20 to 30% demand reduction for that 2-hour period. So it worked effectively. Everything stayed in control, by the way, because we didn't, if you had a zone that had a 72-degree set point, it went to 73. So we didn't say this just turned off or the fan turns off or anything else, but everything stayed under control. But this is still not easy, and it's still not simple. There's challenges with control programming. There's challenges with supporting open standards here. There's challenges with metering. There's challenge with doing this fast. Ideally, a lot of the things that we would do in building to grid would help us manage voltage, frequency, and capacity. But to do that, we have to do things fast. Our control systems are all designed to do things slowly because they don't need to be fast, but they could be. So I did a project on this where we got response time down to 5 seconds just by re-engineering the control network and getting that speed up. We have lack of understanding. We have this whole balance issue between comfort and control. I spend all of my time trying to make people in buildings comfortable, and mainly our strategy here is making them uncomfortable, so we got to balance that out. Bob?
I'm gonna ask you, when you guys are kicking around with the dogs, that's great. Do you guys ever
So the question was, is there thought about isolating out front ends? I would say the thought is just the opposite. The thought with most progressive owners is about integrating, not isolating. And
Open architecture, that's what I'm saying, where there's a standard that everybody plugs in.
you know, a lot of owners today, Bob, are using things like VLANs to isolate out traffic from those individual systems. So for example, your IP cameras may go on a different VLAN so their traffic's isolated out from everything else. That's pretty common. When it makes sense though, people want to integrate. When it doesn't make sense, they shouldn't do it. So for example, the airport project I did, you know, we did integration with the fire alarm system because that was operationally related. Just for data, not just for just read-only information, not for control at all. But it should not impact the performance at all. If it's impacting the performance, something's being done wrong.
Well,
So.
and that's the thing, is that there can always be a finger pointed if you don't have
Yeah.
one central hub.
Yeah. The general system people do is to get every system up and running separately, then integrate it, and then have a way to split it off and test it to see where the problem exists. And that can be hard. I did a refrigeration integration problem where we had a lot of problems and a lot of difficulty troubleshooting it. So it can be difficult. Yeah.
Do
Tom.
you see integration of fire alarm systems, really?
Do I see integration of fire alarm systems really? Sort of is the answer. The only time we see integration of fire alarm systems is for read-only data for status.
Okay.
We don't want it, I will never do integration for control. Yeah, but for operational data, yeah, I'd like to see if there's a smoke detector in the room that's, yeah.
That's the funniest thing. I've had meetings where I found that people's definition of the word integration varies.
Well, that's absolutely true. And many of us, for example, you know, even if I do an integrated system and I integrate, for example, a VFD in my HVAC systems, it's not even fire related, I still will do a hardwired analog signal to control it, even though I integrate it to bring the data back. Just because, once again, we tend to be cautious. So let me kind of wrap up here. So other challenges, we have issues with systems. So thermal systems are great, but they're hard to justify. You've got to have a good business case to do it. I've worked on projects with thermal storage where we've had to mothball them or disable them because they don't work as part of a program anymore. Batteries are a fantastic solution. Batteries are the holy grail here. This is the perfect answer. If batteries were free, we wouldn't need to make buildings smart, but batteries are horrendously expensive and high maintenance and a long-term environmental issue. But when they become free, that will be a fantastic solution. On-site generation used to be the solution for this. I worked with the utility, and their entire demand response program was having commercial owners start up their generators until the EPA changed the requirements that they had to meet the same environmental controls as over-the-road equipment, so that wasn't such a good deal. Plug-in electric vehicle integration, fantastic idea. Wouldn't it be great if you could bring your Tesla in and you could plug it into the grid and it could charge and then discharge as well? Isn't that a great concept? There's not a electric car manufacturer out there today that will allow that, and they may never allow it. And we've talked to the people from GM, we've talked to the people from BMW, and they said, look, this is really simple. Our job is to guarantee the performance of the car to the owner. So we carefully tested, we know what the performance of the battery is, what its charge-discharge cycle is, and what would you like to do? You want to discharge it to feed the grid? I'm not sure that fits in my warranty. It'll happen eventually. High potential, but it's going to be slow to occur. And then we've got to get the business model. This is not free. In fact, it can be pretty expensive. So owners need to have a good model, and they need to be able to justify it, and they need to be able to validate it. So in summary, controls are in a period right now of change. We've got some new technologies. We've got new solutions. We've got new standards coming out. It's pretty exciting. It's pretty cool. We have fantastic potential with controls to do better. We know what we can do with controls. We've done projects where they work really well. It can be really effective, but we're not doing it reliably and consistently. We have challenges largely in the process, in how we do design and deliver it. I love the Best Center because you guys are thinking about how we train technicians and how we train operators and how we make people better at some of these really critical parts. You're not trying to fix everything, but you're fixing some parts that nobody else is thinking about, which is invaluable. And the challenge is how do we transform the industry? And the answer is, back to Bob's point, we need to fix the engineer, we need to fix the products, we need to fix the operators, we need to fix the contractors, we need to fix all of these things. But what you guys are working on at Best Center is just an essential part of getting to what we need for that transformation. That's it.